Master Course Python Programming for Beginners. Welcome to the Master Course Python Programming for Beginners. In this comprehensive course, we will take you from the absolute basics of programming to building your very own interactive applications. Whether you're aiming for a new career or just curious about code, you're in the right place. Let's get started. Module 1. Getting Started with Python. Lesson 1.1. Introduction to Python. Welcome to our first lesson. Imagine you want to talk to a computer, tell it what to do, and have it do amazing things, from organizing your photos to powering your favorite websites. How do you do that? You use a special language, and today we're going to meet one of the most friendly and powerful ones, Python. Think of it as a universal translator that helps you speak to computers. By the end of this lesson, you will be able to define what Python is, its key applications, and its advantages as a programming language. We'll uncover what Python is, explore some of the cool things it's used for in the real world, and understand why it's such a fantastic language for people just starting their coding journey. So what is Python? Python is a popular, high-level programming language. High-level simply means it's designed to be easy for humans to read and write, much like regular English. Created by Guido van Rossum and first released in 1991, it's known for its simplicity and readability. It uses clear English keywords and has fewer complex rules than many other languages, which is why it's often compared to writing regular sentences. And it's used everywhere. In web development, Python helps build the back end of websites and applications. Companies like Instagram, Spotify, and Dropbox use Python in their systems. It's also a powerhouse in data science and machine learning, analyzing vast amounts of data to power things like Netflix's recommendation engine or parts of self-driving cars. It's also brilliant for automation, making your computer do repetitive tasks automatically, like renaming thousands of files or sending automated emails. The advantages are clear. Python is easy to learn. Its simple syntax lets you see results fast. It's incredibly versatile, and it's backed by a large and supportive community, meaning help is always available online. Best of all, it's open source and free, and it runs on Windows, Mac OS, and Linux without needing to be rewritten. To really see its reach, this is a great one to try yourself. Take a moment to research 3 real-world applications where Python is used, perhaps beyond the examples we just discussed. When you do, you'll uncover its role in everything from scientific research at NASA to special effects at Industrial Light and Magic, where Python scripts help automate complex animation processes. So to wrap up this introduction, let's consider why Python is such a popular choice for beginners. The key reason is that its code looks a lot like plain English, making it easy to read and understand. This means new programmers can focus on solving problems rather than getting bogged down by complicated rules. Plus, its versatility and the huge online community make it a supportive and powerful language to start with.
Lesson 1.2. Getting Started and Installation. You've learned what Python is and why it's so great. Now, it's time to get your hands dirty. Before you can start writing your amazing Python programs, you need to set up your workspace, much like an artist needs their brushes and canvas. By the end of this lesson, you will have successfully installed Python and a suitable integrated development environment, or IDE, on your local machine. We will walk through the steps to download and install Python, then install a user-friendly tool called VS Code, which is where you'll write and run your code. Finally, you'll run your very first Python program. You need 2 things: the Python interpreter, which understands your code, and an IDE, which is a special program that makes writing code much easier. We recommend an IDE called Visual Studio Code, or VS Code, because it's free, powerful, and very popular. First, let's install Python. Visit the official Python website at python.org/downloads. Click the button to download the latest version for your operating system. When you run the installer, there's a crucial step for Windows users. Make sure to check the box that says Add Python to path at the bottom of the first screen. Then simply follow the on-screen prompts, choosing the default options. To verify the installation, open your command prompt or terminal, type python-version and press enter. You should see the version you just installed. Next, install VS Code. Visit code.visualstudio.com, download the installer, and run it, again accepting the default options. Once VS Code is open, click the Extensions icon on the left sidebar, search for Python, and install the official extension by Microsoft. This will supercharge the editor for Python development. Now for the moment of truth, your first program. I encourage you to follow these steps to see it working firsthand. In VS Code, create a new file and save it as hello.py. The py is essential. In that file, you'll want to type this simple command: print hello world. Now, click the small play button in the top right corner. When you run this, you'll see Hello World appear in the terminal window at the bottom of VS Code. Congratulations! You've just run your first Python program. The ideal result of this setup process is having a program file on your computer named myfirstpythonprogram.py with the code print hello Python beginner and seeing the output hello Python beginner displayed in your terminal. This confirms your entire setup is working perfectly.
Lesson 1.3: Basic Code and Drawing a Shape. Now that your environment is set up, it's time to start talking to the computer. Just like you learn individual words and then put them into sentences, we'll start with the most basic words in Python. By the end of this lesson, you'll be able to write and execute basic print statements and understand the concept of sequential execution. We'll explore the print function and see how computers execute instructions in order, one by one. The print function is your program's voice. It allows your program to display text, numbers, or other information on the screen. Whatever you want to display goes inside the parentheses, and if it's text, you must enclose it in quotation marks. For example, print hello will display the word hello on the screen. Computers are very literal. They read and execute your code from top to bottom, one line at a time. This is called sequential execution. It's like a recipe. You complete the first step, then the second, and so on. For example, in this code block, print step 1, get out of bed. Print step 2, brush your teeth. Print step 3, eat breakfast. The computer will print these messages in this exact order. We can use this concept to create simple ASCII art, which uses characters to create images. To really solidify this, here's a fun shape to create. I encourage you to write a Python script with the following commands: print asterisks, print asterisks, print asterisks, print asterisks. When you run this, Python executes each print statement in sequence, and the output clearly shows you a simple square made of asterisks. For a final check on this concept, consider the code to draw a simple triangle. The correct code would use 3 print statements executed in order to form the shape, like so: print //, print / space // print /__.
Lesson 1.4: Variables. Imagine you're writing a story. It would be tedious to type a character's full name and age every time you mention them. What if you could give each piece of information a special label, and then just use that label? That's exactly what variables do in programming. They're like labeled boxes where you can store information. In this lesson, you'll learn to define, declare, and assign values to variables in Python. A variable is a named storage location in your computer's memory. You create one and give it a value using the equal sign, known as the assignment operator, like this: variable name equals value. For example, name equals Alice stores the text Alice in a variable called name. Age equals 30 stores the number 30. There are a few rules for naming variables. They can only contain letters, numbers, and underscores, but they cannot start with a number. They are also case-sensitive, so age is different from age. Best practice is to use lowercase letters with underscores to separate words, like first underscore name. This is called snake underscore case. Variables can hold different types of data. The most common are strings for text, integers for whole numbers, floats for numbers with decimals, and booleans, which represent true or false. You can use variables directly with the print function to display their stored value. Here's a great exercise to try. Create a Python script and declare 3 variables, one for your first name, one for your age, and one for your favorite hobby. Then use these variables in a print statement like this. Print, hello, my name is, first name, I am, age, years old, and I love, favorite hobby. The output will be a personalized sentence constructed from the values stored in your variables. Now, let's test our knowledge of variable naming rules. Consider these names: underscore my variable, first underscore lesson, user underscore name, age, and if, which are invalid. Well, first underscore lesson is invalid because variable names cannot start with the number. User underscore name is invalid because it contains a space. And if is invalid because it's a reserved Python keyword. The others are perfectly valid.
Lesson 1.5. Working with strings. Your name, a sentence, an entire book. In Python, all of this is text, which we call strings. Just like you can cut, paste, or combine words in real life, Python gives you powerful tools to manipulate text. In this lesson, we'll learn to manipulate string data using common methods like concatenation, slicing, and case conversion. A string is a sequence of characters enclosed in quotes. String concatenation means joining strings together, which we do with the plus operator. For example, full name equals John plus a space plus Doe combines 3 strings to create the full name, John Doe. Strings are also like a list of characters where each character has a position, or index, starting from 0. We can slice a string to get a portion of it using square brackets. For the word Python, word 2:5 gives you the characters from index 2 up to, but not including, index 5, resulting in tho. Python also has built-in methods to easily change a string's case. .upper converts to uppercase, .lower to lowercase, and .capitalize makes the first letter uppercase. Finally, the len function will tell you how many characters are in a string. I encourage you to run this next program to see these features firsthand. The goal is to ask a user for their first name and last name, and then display their full name, their initials, their full name in uppercase, and the total number of characters. When you run this, you'll see how combining concatenation and slicing, for example, first name 0 and last name 0, can easily produce the user's initials. The output will reveal a formatted summary of their name information. To really solidify this, let's look at a few operations. Given the string language equals Python programming, what would be the output? Print language.lower would output Python programming. Print language 7 to 18 would slice the string to output programming. And print I love plus language 6 would concatenate I love with the first 6 characters of language, resulting in the output I love Python.
Lesson 1.6, Working with Numbers. Computers are brilliant at math. Numbers are everywhere in programming, and this lesson will show you how Python handles them. Our objective is to perform basic arithmetic operations with integers and floats and understand type conversion. We'll explore whole numbers and decimals, learn how to do math with them, and discover how to change a number from one type to another. Python has 2 main types of numbers: integers, or int, for whole numbers, and floats for numbers with the decimal point. Python uses familiar symbols for math. plus for addition, minus for subtraction, asterisk for multiplication, and slash for division. It also follows the standard order of operations, often remembered by the acronym PEMDAS. Sometimes you need to convert between number types. The int function converts a value to an integer, cutting off any decimal part. The float function converts a value to a float. This is crucial when you're working with text that represents a number. For example, int parentheses 50 will turn the string 50 into the integer 50, allowing you to perform calculations with it. Be careful though. You cannot add a number directly to a string. You must first convert the number to a string using the str function. This is a great one to try yourself in your lab. I encourage you to write a script that calculates the area and perimeter of a rectangle. You'll want to create two variables, length and width. Calculate the area as length times width and the perimeter as 2 times parentheses length plus width. When you run this, you'll print both results with descriptive labels, and you'll see the calculations performed correctly even with a mix of integer and float values. Let's check our understanding. What's the output of print 17/5? The answer is 3. This is floor division, which always rounds down. What's the output of print 7% 2? The answer is 1. This is the modulus operator, which gives the remainder of a division. And finally, what happens if you run print result plus 10? This would cause a type error. The fix is to convert the number to a string. Print result plus str10.
Lesson 1.7. Input from user. So far, our programs have been a monologue. But what if you want your program to be interactive and ask the user for information? This is where getting input from the user comes in. In this lesson, our objective is to obtain input from the user using the input function and convert it to appropriate data types. The input function pauses your program and waits for the user to type something and press enter. Whatever the user types is returned as a string. You can provide a message inside the parentheses to prompt the user. For example, the code name equals input, what is your name, will display what is your name and wait. If the user types Alice, the variable name will hold the string Alice. A critical point to remember is that user input is always a string. Even if the user types the number 25, Python sees it as the string 25. If you want to perform calculations, you must convert it to a number using int or float. You can even combine these steps on one line, like this. Age equals int, input, how old are you? To really solidify this concept, here's a short program you'll want to run. Ask the user for their favorite color and their lucky number. Store both in variables, making sure to convert the lucky number to an integer. Then, print a personalized message combining both. When you run this, you'll see a message like, "Your favorite color is blue, and your lucky number is 7. What a great combination!" To conclude, let's complete a simple program. We want to ask for a user's height in centimeters and print it in meters. Here's the code with blanks. Height centimeter string equals input, enter your height in centimeters. Height centimeter number equals blank, height centimeter string. Height underscore m equals height centimeter number slash 100. Print, your height in meters is blank. The solution is to fill the first blank with float, as division can result in decimals. The second blank should be filled with height m, the variable holding the final result. The corrected code will now work perfectly. This concludes our first module. You've learned what Python is, how to set up your environment, write basic instructions, use variables, manipulate text, perform calculations, and interact with the user. These are the absolute bedrock of all programming. Module 2.
Building simple programs. Lesson 2.1. Building a basic calculator. Welcome to Module 2. You've learned about variables, numbers, and user input. Now let's put them all together to create a useful tool, a basic calculator. This will be the first time you see individual concepts working together to solve a real problem. Our learning objective is to combine user input, numeric operations, and print statements to create a functional calculator that can add two numbers. The plan is simple. First, we'll greet the user. Then, we'll ask for two numbers, making sure to convert their string inputs into floats. After that, we'll add the two numbers together and store the answer. Finally, we'll display the result in a clear, readable way. This program demonstrates the full input, process, output cycle. We take raw data from the user, process it by converting types and performing a calculation, and then give back meaningful information. To take this further, I encourage you to build this program yourself, but with a twist. Make your calculator perform multiplication instead of addition. The logic is nearly identical. You'll simply change the plus operator to a star. The result will be a user-friendly program that multiplies any two numbers you provide. Now, let's try some debugging. Here is a broken calculator script meant to perform subtraction. There are two errors. The first is that the inputs num1 and num2 are strings, and you can't perform subtraction on text. The fix is to convert them to numbers using float. The second error is in the final print statement, which tries to add a string to a number. The fix is to either convert the result to a string using str, or, more simply, use a comma to separate the items in the print function. With those changes, the calculator works perfectly.
Lesson 2.2. Creating a Mad Libs game. Let's switch from math to wordplay. Mad Libs is a fun game where you insert random words into a story, often with hilarious results. Building one in Python is a perfect way to practice working with strings and user input. Our objective is to utilize string concatenation and user input to construct a simple text-based game. The recipe for this game is straightforward. First, we come up with a story template with blank spaces. Then, for each blank, we use input to ask the user for a specific type of word, like a noun or a verb, storing each in a variable. Finally, we use string concatenation with the plus operator to build the final story, inserting the user's words. This project is a fantastic exercise in string manipulation, showing how programs can generate custom content based on user input. This is a great one to try building yourself. I encourage you to program your own Mad Libs game. Create a unique story template with at least 4 blank spaces, perhaps an adjective, a noun, a verb ending in ing, and a place. Prompt the user for each word and then print their custom story. The output will be a unique and likely funny story you've generated together with your program. Now let's review a snippet of code. Does it work correctly? Yes, it does. But how could we make the final output more readable? A simple improvement would be to add a blank line using \n before printing the final story. This separates it visually from the input prompts. You could also add a title like Your Story to make the output even clearer. Great work! You have now built 2 complete programs from scratch, combining the building blocks from Module 1 to create both a practical tool and a fun game. You're starting to think like a programmer.
Module 3. Understanding Python Data Structures, Sequences. Lesson 3.1. Lists. Welcome to Module 3. Imagine you need to make a grocery list. You'd write all the items down on one list. In Python, when you need to store a collection of related items, you use a list. It's a single container that can hold multiple items in order. In this lesson, we will learn to define and create lists, access elements by index, and understand that lists are mutable, meaning they can be changed. A list is an ordered,
changeable collection of items created by placing items inside square brackets separated by commas. For example, shopping list equals milk, eggs, bread. Each item in a list has a position called an index, starting from 0. You use square brackets with the index number to get the item at that position. For example, shopping list 0 would give you milk. You can also use negative indexes to count from the end. So shopping list -1 would give you bread. The most important feature of lists is that they are mutable, which means you can modify them after they've been created. To change an item, you access it by its index and assign a new value. For example, the command mylist1 equals 25 would change the second item in my list to the number 25. I encourage you to try this yourself. Create a list of your 3 favorite fruits. Print the entire list, then print just the first fruit using index 0 and the last fruit using index -1. Then change the second fruit in the list to something different. When you print the modified list, you'll see the change reflected instantly, demonstrating the power of mutability. To check our understanding, let's consider the list colors equals red, green, blue, yellow. What code would print green? The answer is print colors 1. What is the index of yellow? It's 3. And what code would change blue to purple? That would be colors 2 equals purple.
Lesson 3.2, List Functions. You've created a list, but what can you do with it? You need to be able to add new items, remove items, or sort the list. Python gives you special actions called functions and methods to manage your lists. In this lesson, we will apply common list methods such as append, insert, remove, pop, and sort. First, the len function tells you how many items are in a list. To add items, you have 2 options. The .append method adds an item to the very end of the list. The .insert method adds an item at a specific index. To remove items, .remove searches for the first occurrence of an item and removes it by its value. Alternatively, .pop removes an item at a specific index. Finally, the .sort method sorts the list in place, alphabetically for strings, or in ascending order for numbers. Here's a great way to practice these functions. Imagine managing a party guest list. Start with a list containing Alice and Bob. I encourage you to run these commands in sequence. First, append Charlie to the end. Then, insert David at the beginning at index 0. Next, remove Bob. Finally, sort the list alphabetically. When you're done, the final sorted guest list will show Alice, Charlie, David, and the total number of guests attending will be 3. To conclude, let's write a simple program to manage a to-do list. The task is to start with a list containing pay bills and go to grocery. Then, add a new task, call mom, to the end, and finally, remove pay bills. The correct sequence of commands would be creating the list, then to-do list.append call mom, followed by to-do list.remove pay bills. The expected output would be a new list containing just go to grocery and call mom.
Lesson 3.3, Tuples. We now have lists, which are great for collections of items that change. But what about data that should never change, like the months of the year or the coordinates of a specific location? For these situations, Python gives us a special type of list called a tuple. Our goal in this lesson is to define and create tuples and understand their key feature, immutability. A tuple is an ordered, unchangeable collection of items. You create a tuple by placing items inside parentheses, like this. Coordinates equals 40.7128, -74.0060. Like lists, you can access elements by index and find their length with len. However, the key difference is that tuples are immutable. You cannot modify a tuple after you've created it. If you try to change an item, Python will give you a type error. This is a safety feature that prevents accidental changes to important data. We use tuples for data integrity, when we have data that must remain constant. To really see immutability in action, I encourage you to try an experiment designed to fail. Create a tuple that represents a geographical coordinate. Print the first item. Then, try to write a line of code that changes the second item. When you run this, you won't see an output. Instead, you'll see a type error from Python, proving that the data inside the tuple is protected from modification. So what's the main difference between a list and a tuple? A list is mutable, meaning it can be changed, while a tuple is immutable, meaning it cannot. You would use a list for a collection that needs to change, like a list of players in a game. You would use a tuple for data that should remain constant, like the days of the week or the fixed RGB values for a specific color. Excellent. You now understand how to store collections of data using lists for changeable data and tuples for unchangeable data. This is a huge step up from working with single variables.
Module 4. Functions for Reusability. Lesson 4.1. Functions. Welcome to Module 4. Imagine you have a task you need to do over and over again. Repeating code is tedious and error-prone. A function is like a recipe. You define the steps once, give it a name, and then you can call that recipe anytime you need it. Our objective is to learn how to define and call our own custom functions, pass data into them as arguments, and understand the concept of code modularity. Functions help you follow the don't repeat yourself or dry principle. They also help organize large programs into smaller, manageable chunks. You define a function using the def keyword, followed by a function name, parentheses, and a colon. The code that belongs to the function is indented below it. For example, def say hello, print hello world. Defining a function doesn't run it. To execute the code, you must call the function by writing its name with parentheses, like say hello, parentheses. We can make functions more flexible by passing data into them. The variables inside the function's parentheses are called parameters. The actual values you pass in when you call the function are called arguments. For example, def greet name. Print hello plus name plus exclamation point. Greet Alice. Here, name is the parameter and Alice is the argument. The output will be hello Alice. To practice this, I encourage you to write a function named displayFavoriteFood. This function should take one argument, food name, and print a sentence like, my favorite food is food name. When you call this function 3 times with 3 different foods, your output will be 3 personalized sentences, demonstrating the reusability of your function. Now, let's complete a function that calculates the area of a rectangle. Here's the code with blanks. Def blank length width area equals length times width. Print the area is blank. Blank 5, 4. The first blank should be the function name, calculate area. The second blank is the variable we want to print, area. And the final line should be the function call, calculate area 5, 4. This creates a reusable tool for calculating area. Lesson 4.2. Return statements. Our functions so far have performed actions like printing to the screen. But what if you need a function that produces something you can use later? The return statement is how a function gives back a result. Our learning objective is to use the return statement to send values back from a function, allowing them to produce results that can be used elsewhere. Print is for display only. Return sends a value out of the function back to the line of code that called it. This allows the program to use the result.
When Python sees return, it immediately stops the function and sends the specified value back. We typically capture this returned value in a variable. Consider a function add and return a, b that returns a plus b. We can call it and store the result. Sum result equals add and return 5, 3. The variable sum result will now hold the number 8, which we can use for further calculations like sum result plus 10. This makes functions powerful building blocks. Let's practice this. In the previous lesson, you created a greetName function. I encourage you to modify it. Instead of printing the greeting, have it return the message string. Then call the function, store its returned value in a variable called message, and finally print that variable. You'll see the same output, but your code is now much more flexible and modular. To assess this concept, let's write a function named square that takes one number as a parameter. The function should calculate the square of that number and return the result. The solution would look like this. Define square number, return number times number. Squared value equals square 7. Print squared value. This code defines the function. It then calls the function with the number 7, stores the returned value, which is 49, in the squared value variable, and prints it. The expected output is 49. Congratulations on mastering functions. You now know how to package your code into reusable blocks, make them flexible with parameters, and get results back from them using return.
Module 5. Controlling Program Flow. Conditionals. Lesson 5.1, If Statement. Welcome to Module 5. Until now, our programs have been a straight road, executing every line from top to bottom. But life is full of choices. What if you want your program to make a decision? The if statement is our first tool that allows our program to choose which path to take. Our objective is to implement if statements to execute code blocks conditionally. The if statement checks if a condition is true. If it is, the indented code block below it is executed. If the condition is false, the block is skipped entirely. The syntax is the keyword if, followed by the condition and a colon. Remember, we use a double equal sign equals equals to check for equality. For example, if the variable is raining is true, the program will print don't forget your umbrella. If is raining is false, that line is skipped and only the final have a nice day message is printed. This is the core of decision-making in code. To see this in action, this is a great one to try yourself. Write a program that has a variable user age set to a value like 20. Then write an if statement, if user age greater than or equal to 18. Within that if block, print the message you are eligible to vote. When you run this, because 20 is greater than or equal to 18, the condition is true, and the output you'll see is you are eligible to vote. Now, what will the following code snippet print? Temperature is 15. If temperature is greater than 25, print it's a hot day. Print end of program. It will only print end of program. The condition temperature is greater than 25 is false, since 15 is not greater than 25. Therefore, the indented line is skipped.
Lesson 5.2, If Statements and Comparison. The simple if statement is great, but decisions are often more complex. What if you want to handle multiple scenarios? The if-elif-else structure lets you build a chain of logic. In this lesson, we will use comparison operators within if, elif, and else statements to handle these multiple conditions. We have a full set of comparison operators: equals, equals to equals, not equal to, and less than, greater than, less than or equal to, and greater than comparisons. We can use these with two new keywords. The else statement provides a block of code to run when the if condition is false. Elif, short for else if, allows you to check for another condition if the first if was false.
In a grading example, the code checks the score from top to bottom. It will execute the code for the first condition it finds to be true and then skip the rest of the chain. For a score of 85, it skips the A grade condition, finds the B grade condition to be true, prints grade equals B, and then skips the rest of the chain. I encourage you to build a program that uses this structure. Ask the user to input a number. Then use an if-elif-else chain to check the conditions if number greater than 0, elif number less than 0, else. When you run this, the output will correctly identify whether the number is positive, negative, or 0, demonstrating a complete decision-making process. To test our understanding, let's consider the logic for a leap year program. A leap year is divisible by 4, except for century years, which must be divisible by 400. The ideal solution involves nested if statements. The outer if checks if year %4 equals 0. Inside that, you would have another if-else block to handle the special century year rule, correctly identifying all leap year cases.
Lesson 5.3. Better Calculator. Remember the basic calculator we built? It could only perform addition. Now that we know how to make decisions, we can upgrade it to be much more powerful. Our objective is to enhance our calculator by incorporating if-elif-else statements to handle different arithmetic operations chosen by the user. The new plan is to ask the user for two numbers and an operator symbol, plus, minus, multiply, or divide. Then we'll use an if-elif-else chain to check which operator the user entered and perform the corresponding calculation. If they enter an invalid operator, the else block will catch it and print an error message. Now it's your turn to refactor your own calculator. This is a great one to try yourself in your lab. Rebuild your calculator using the if-elif-else structure. As a challenge, add a check for division by 0. Inside the elif op equals / block, you'll want to add a nested if statement. If num2 equals 0. If this condition is true, print an error message. When you run this, your calculator will now be robust. The output will either be the correct calculation or a helpful error message like error cannot divide by 0. The final assessment for this is to test your new calculator. For an input of 5 plus 3, the output should be 8.0. For 10 divide 2, the output should be 5.0. For an invalid operator like %, the output should be invalid operator entered. And for a division by 0, like 8 divide 0, the output should be your specific error message. Fantastic! Your programs can now think and make decisions, a cornerstone of programming that enables dynamic and responsive applications.
Module 6. Understanding Python Data Structures, Mappings. Lesson 6.1. Dictionaries. Welcome to Module 6. We've learned about lists, which are great for ordered items accessed by their numerical index, but what if you want to look up information using a specific label, like in a real dictionary? In Python, a dictionary lets you do exactly that. It stores information as pairs of a key, the word, and a value, the definition. Our objective is to define and create dictionaries, access values by keys, and manage their contents. A dictionary is an unordered, changeable collection that stores data in key-value pairs. You create one using curly braces. Each item consists of a key, a colon, and a value. Keys must be unique. For example, phone book equals Alice, 555-1234, Bob, 555-5678. To access a value, you don't use a number, you use the key inside square brackets. Phone book Alice would give you 555-1234. Dictionaries are mutable. To add a new entry, you simply assign a value to a new key. To modify an existing one, you reassign the value for that key. To remove a pair, you use the del keyword. To really solidify this concept, here's a profile you'll want to create. Build a dictionary representing your personal profile with keys for name, age, city, and favorite food. I encourage you to run commands to print your city, then add a new key for your favorite color, and finally change your favorite food. When you print the final dictionary, the output will reveal the fully updated profile, showing how easily dictionaries can be managed. Let's conclude with a small program. The task is to create a dictionary to store the number of days in 3 months, January, February, and March. Then ask the user to enter a month's name. The ideal solution is to use the user's input string as the key to look up the value in your dictionary. For an input of February, the code days equals month days, February would store 28 in the days variable, which you would then print. Well done! You now understand dictionaries, a powerful key value system used extensively in programming for everything from configuration files to representing complex objects.
Module 7. Controlling Program Flow. Loops. Lesson 7.1. While Loop. Welcome to Module 7. Imagine you need to hammer in 10 nails. You wouldn't write down, hit the nail, 10 times. You'd think, while there are still nails left, hit the next nail. A while loop does exactly this in programming. It allows you to repeat a block of code as long as a certain condition remains true. A while loop has 3 parts. First, an initialization, where you create a variable to control the loop. Second, the condition in the while statement that's checked on each iteration. And third, an update step inside the loop that changes the variable so the loop can eventually stop. If you forget the update step, you create an infinite loop where the program runs forever. In a countdown example, count is initialized to 5. The loop continues while count is greater than 0. Inside the loop, count is printed, and then it is updated by subtracting 1. Once count reaches 0, the condition becomes false, the loop stops, and blastoff is printed. I encourage you to run this next command to see the power of this feature firsthand. Write a program that uses a while loop to print the numbers from 1 to 10. You will need to initialize a counter to 1, loop while counter equals 10, and inside the loop, print the counter and then add 1 to it. When you run this, the output should clearly show you the numbers 1 through 10 printed in order, demonstrating a perfect loop structure. Now, let's debug. The following code is supposed to print still running 3 times, but it contains an infinite loop. The error is that the variable I is never updated. The fix is to add I equals I plus 1 inside the loop. With this change, the loop will correctly run 3 times and then stop. Lesson 7.2. Building a guessing game. Let's build something really fun that combines everything we've learned. A number guessing game. The computer will think of a secret number and the user has to guess it. The while loop is the perfect engine for this. While the user's guess is not the secret number, keep asking for another guess. Our objective is to combine loops, conditionals, and user input to create this interactive game. The logic is simple. We'll set a secret number. Then we'll start a while loop that continues as long as the user's guess is not equal to the secret number. Inside the loop, we'll ask the user for their guess. We'll then use if-elif statements to provide too low or too high hints. Once the loop finishes, it means the user guessed correctly and we'll print a "You win" message. This is a great one to build yourself. I encourage you to create the guessing game as described. As an added feature, create a guess count variable that starts at 0. Inside the loop, add 1 to it each time the user guesses. When the user wins, the output can reveal not only that they won, but also how many guesses it took them. Now, an important assessment of your game. What happens if the user enters text like "hello" instead of a number? The program will crash with a value error. This happens because the line guess equals int of input tries to convert the text hello into an integer, which is impossible. We'll learn how to handle errors like this later, but for now, it's important to recognize the cause.
Lesson 7.3, For Loop. The while loop is great when you don't know how many times you need to loop.
But what if you do? For example, if you want to do something for each item in a list. For these situations, Python has a more elegant solution, the for loop. Our objective is to implement for loops to iterate over sequences like lists and strings. A for loop is used for iterating over a sequence. The syntax is for item variable in sequence. On each iteration, the item variable automatically takes on the value of the next item in the sequence. You can loop through a list of fruits or even loop through each letter in a string. When you need to repeat an action a specific number of times, we use the range function. Range of 5 generates a sequence of numbers from 0 up to, but not including, 5. This is perfect for loops. For example, for underscore in range of 3, print hello. We'll print hello 3 times. We use an underscore as the variable name by convention when we don't need to use the loop counter itself. To really solidify this concept, here are 2 loops you'll want to run. First, create a list of your favorite hobbies and use a for loop to iterate through it, printing I enjoy hobby for each one. Second, write another for loop that uses range to count down from 5 to 1. The output will demonstrate both iterating over a list's contents and looping a specific number of times. For your assessment, write a program that uses a for loop to calculate the sum of all numbers in a list without using the built-in sum function. The ideal answer involves initializing an accumulator variable total to 0 before the loop. Then, for each number in the list, you add it to the total. After the loop finishes, you print the total. For the list 1, 5, 10, 4, 3, the result is 23.
Lesson 7.4, Exponent Function. We know that 2 star 3 gives us 2 to the power of 3. But how does that actually work? It's just repeated multiplication. We can build our own function that does this using a loop, combining our knowledge of functions and loops to build a useful tool from scratch. The logic is as follows. We'll define a function that accepts a base number and a power number. Inside, we'll initialize a result variable to 1. Then we'll create a for loop that iterates power number times. Inside the loop, we'll multiply our result by the base number. After the loop finishes, we return the final result. Testing this with power function 2, 3 will correctly return 8. I encourage you to implement the power function yourself. Test it with several different numbers. As an interesting case, what does your function do if the power number is 0? The range 0 function creates an empty sequence, so the loop never runs. The function will immediately return the initial value of result, which is 1. This is the correct mathematical answer for any number to the power of 0. Now, how would you modify the function to handle a negative base number? Let's test power function -3, 2. The current code already handles it correctly. The loop runs twice. The first time, result becomes 1 times -3, which is -3. The second time, result becomes -3 times -3, which is 9. The function correctly returns 9.
Lesson 7.5, 2D list and nested loops. We know how to store items in a one-dimensional list, but what if you need to represent a grid like a tic-tac-toe board or a spreadsheet? For this, you need a 2D list, which is simply a list that contains other lists. To work with these grids, you need a loop inside another loop called a nested loop. A 2D list is a list of lists where each inner list represents a row. You access elements using 2 sets of square brackets, list, row index, column index. To iterate through every element, you use an outer loop for the rows and an inner loop for the items within each row. The outer loop gets the first row, 1, 2, 3, then the inner loop runs completely, printing 1, then 2, then 3.
After the inner loop finishes, the outer loop moves to the next row and the process repeats. To really see the structure, here's the grid you'll want to build. Create a 3x3 tic-tac-toe board using a 2D list, initially filled with dash strings. Then use nested for loops to iterate through the board and print each element. A small trick is to use print element and equals space inside the inner loop to print without a new line, and a blank print after the inner loop to move to the next line. The output will be a perfectly formatted 3x3 grid on your screen. Incredible! You have now mastered loops, one of the most powerful concepts in programming. The combination of conditionals and loops forms the core logic of almost every program you will ever write.
Module 8, Advanced Projects. Lesson 8.1, Building a Translator. Welcome to our final module. Let's create another fun project, a secret language translator. The idea is simple. We'll create a rule, for example, all vowels become the letter G, and apply it to any sentence. This project is a fantastic way to practice string manipulation, loops, and conditional logic, all at once. The logic is this. We'll define a function that takes a phrase. We'll create an empty string called translation. Then we'll loop through each letter of the input phrase. Inside the loop, we'll use an if statement to check if the letter is a vowel. If it is, we'll add a G to our translation string. If it's not, we'll add the original letter. After the loop, we return the final translation. This code can even be written to preserve the case of the original letters, making it a robust little translator. I encourage you to implement this translator function. Test it with various phrases. Can you think of another simple secret language rule? Try modifying your function to implement a different rule, for example, doubling every consonant. This is a great way to experiment with the logic you've built. Let's assess one key part of the code, letter.lower in vowels. How does this work? First, letter.lower converts the current letter to its lowercase form. Then, the in keyword checks if that lowercase letter exists anywhere inside the vowel string A-E-I-O-U. This is a great strategy because it allows us to check for both A and A with a single condition, making the code much simpler.
Lesson 8.2 and 8.3, Class Projects. This is it. You've learned all the fundamental building blocks of Python. Now it's time to put it all together and become a true creator. For the rest of this module, you will choose, design, and implement your own small-scale Python projects from scratch. Your objective is to independently design and implement projects that integrate at least 3 core concepts from the course. Every developer follows a workflow. First, choose a project. Second, plan your logic in plain English before writing code. Third, build the code, translating your plan one step at a time. Fourth, test your program with different inputs to try and break it. And fifth, debug any errors you find. We have a list of project ideas for you to choose from. You could build a dice rolling simulator using the random module, or a basic password generator, also using random. You could create a unit converter with functions for each conversion and an if-elif-else chain to select them. Or you could build a classic rock, paper, scissors game against the computer. To put your knowledge into practice, your final activity is to complete 2 of these projects. Choose one to start with, plan it, code it, and test it. For your second project, try to choose one that's slightly more complex or add a new feature to it. For example, after building the dice roller, try the rock, paper, scissors game and add a loop so the user can play multiple rounds. This is your chance to solidify your skills by building something completely on your own.
Your final assessment for this course is to submit the Python code files for both of your completed projects. The code should be well commented, organized into functions where appropriate, and should successfully accomplish the goals of the projects you chose.
Course conclusion. Congratulations! You have completed the Python Programming for Beginners Master Course. You began this journey with the fundamental question, what is Python? And have progressed all the way to building your own functional applications from scratch. You have learned to speak the language of Python, mastering its syntax, variables, and data types. You can store data in powerful structures like lists and dictionaries. You can control the flow of your programs, making decisions with if-else statements and automating repetition with for and while loops. Most importantly, you can build with blocks, writing reusable, organized code with functions to solve real problems. Programming is a skill that grows with practice. The journey doesn't end here. Continue to build small projects, explore new Python libraries, and challenge yourself with new problems. You have built a rock-solid foundation, and now you are ready to explore the vast and exciting world of software development. Keep coding.